Welcome to the course on Fourier analysis. So this would be maybe 30 or more lectures. We will cover introductory Fourier analysis, starting from definition of Fourier transform on Rn, and we will study the properties of the Fourier transform. We will also do some interpolation theorems, and then we will finish the course with some results on singular integrals. Okay. Along with we will also see something about harmonic functions on Rn and things like that. This is the first lecture, and this is going to be rather elementary. I am going to recall various things from function analysis, but this would be whatever we would use in the later lectures. Okay, so more about approximate identity, convergence results, and so on. Okay, all right. So let us start. So first thing is polar coordinates on Rn, something which you are of course familiar with. Rn. Okay. So what do? We have a vector, a point in Rn. Okay. So you transform this into R. Well, I will say theta 1, theta 2, etc. up to theta n minus 1, right. So n other functions, right. So the x1 is written as R cos theta 1. Okay. X2 of the same equal to R sin theta 1 cos theta 2, etc., etc. Okay, so the general element is xk. Okay, so this is equal to R sin theta 1, sin theta 2, etc., etc. sin theta k minus 1 cos theta k. So we go from 2 less than to k less than to n minus 2, and of course the last one xn. This is R sin theta 1, etc., etc., etc. sin theta n minus 1, right, where the range of theta is between 0 and pi for k equal to 1, 2, etc. up to n minus 2, and of course the last one goes all the way to 2 pi, right. So, and well, what is R? R is mod x, right. So, R is mod x, which is mod x1 square plus x2 square plus xn square to the half, right. So, this is something which is standard. Okay, we will use this. Well, we use this to transform integrals on Rn to integral over 0 infinity and various ranges of theta, right. So, if I have a suitable function f, okay. So so think of this as a map from Rn to whatever the range here is. You have a Jacobian which gives r to the n minus 1 and various things in theta 1 up to theta n minus 1. So that gives me the Jacobian, which allows me to transform the integrals. Okay. So integral over Rn f of x dx, right. So that is going to be written in terms of r theta 1, theta 2 up to theta n minus 1, right. That is what you do in change of variable. So this becomes integral 0 to infinity. So that is the range for r, and you have the other ranges, right, up to. So I will just copy it down. Well, one can write this as integral over Sn minus 1, that is the sphere in Rn f of r w d sigma w. I'll explain all this times r to the n minus 1 dr. So what is Sn minus 1? This is the sphere in Rn, right, the unit sphere in Rn, which is parameterized by all the theta 1, theta 2 up to theta n minus 1, right. In R2 you have just one theta, right, which goes from 0 to 2 pi, that is the last one. So, well, r to the n minus 1 dr times all those things would be the Jacobian. So, this is the integral which is integral over all those theta. So, let me write it down separately, where integral over Sn minus 1 f of r omega d sigma omega is the n minus 1 etc 0 to pi, and there is 1 0 to 2 pi, right, f of, so I won't write the whole thing. You have sine theta 1 to the n minus 2, sine theta 2 to the n minus 3, etc etc. Okay, so that is the Jacobian, sine theta n minus 2. Okay, and of course d theta 1, etc d theta. So, this is the integral over the sphere. Okay, so in the easiest case is R2, where you will have S1, which is just 0 to 2 pi f of, so you have r cos theta, r sin theta, and d theta, right. D sigma is this measure, okay, whatever is here, and r dr, right, that is what you do in R2. Okay. Well, one thing to note is that this is a rotation invariant measure, okay, rotation invariant measure on Sn minus 1. Okay, it's rotation invariant because dx, the Lebesgue measure, is rotation invariant, and so when you do the polar coordinates, you will get something which is invariant under rotation. Okay, so this is the first thing you need to know, because whatever computation you want to do on Rn, one of the ways to restrict or simplify this would be to go down to polar coordinates and do, especially when the function is radial, for example. The function is radial means it depends only on the distance from the origin. That means the function of r, the omega doesn't, there is no angular change, so omega does not matter, so that would be a finite quantity, and you will have an integral from 0 to infinity. Okay. So, let me give you some easy exercises here. So, use polar coordinates to justify all this. Okay, so this will give you class of functions which are in L1 and etc. So, look at indicator of, let's say, mod x less than to 1 times mod x to the a. Okay, so this is a function on Rn, right? This is just a characteristic function of the unit ball, and I am restricting the function mod x to the a to the unit ball. Right. So, that is my function. This is a radial function. So, if I integrate, I am going to get integral 0 to infinity, and the integral over Sn minus 1 is a finite quantity which has nothing to do with this, because this is mod x, right. This is a function on a function of r. So, you will get r to the a and r to the n minus 1 and dr. So, you can compute the integral as usual and see when it is finite. Okay. So, this would be in L1 of Rn. So, I assume that you are all comfortable with L1, right, Lebesgue integrable functions. This happens if and only if a is greater than minus n. Okay. Well, so this is near 0. At infinity, it behaves exactly the opposite way. So, let me write down that as well. So, if I look at mod x greater than or equal to 1, okay, so that is the characteristic function of the complement of the unit ball times mod x to the a. Well, at infinity it should decay, right. So, a should be as negative as possible. So, that is in L1 of Rn if and only if a is less than minus n, right. So, it is like 1 by x or power more than 1 in the real line, and similarly near 0 it should be less than 1, right, near the. So, that is all is written there. Okay, so, all that will follow immediately by using the polar coordinates. So, notice that the total measure of Sn minus 1. So, if I put f equal to 1, right, this is the integral over the sphere. So, if f is 1, then I am going to get 0 to pi, etc., and then some sine function, cos functions, and so on. So, that is a finite integral. Okay. So, the rotation invariant measure gives a finite quantity to the sphere Sn minus 1. So, whenever I integrate a radial function, this portion does not cause any trouble. That is a finite quantity which is the volume of Sn minus 1 that will come out, and you look at the integral from 0 to infinity. Okay, so this is how you compute. So if you have not done this before, this is a easy exercise. So this is the first thing we need. Second thing is convolution. Okay, on Rn. So it's not just well, I'll define convolution, and we also need various properties of the convolution. Okay. So let's start with the easy one. So take f and g both in L1 of Rn. Okay. Define the convolution of f and g to be, so this is going to be a new function defined on Rn. So f convolve with g at x. Okay. So this is equal to integral over Rn f of x minus y gy dy. Well, this is also equal to integral over Rn f of y g of x minus y dy, okay, which is g convolve with f. Okay. So there are certain things which I am not explaining. F of x minus y gy should be a measurable function for you to integrate, but those are all simple exercises. Well, the interesting fact is that if I take two L1 functions, the product need not be an integrable function, but when I translate and take the product and integrate, it's going to be finite almost everywhere. Okay, so that is what we will see. So let me justify all that. So the convolution defined there, I'll sort of modify it later on when we start Fourier analysis. Right now, let's just stick to that definition. Okay. So we'll put in a constant later. So f convolve with g is that. So if I look at modulus of f convolve with g at x. So I take the modulus there, take it inside, right? So this is going to be less than equal to integral over Rn. This is this integral. F convolve with g comes with another integral. Take the modulus inside, right? So I'll have integral over Rn mod f of x minus y, right? Mod gy dy dx, right? So this is, well, one should start with modulus of f of x minus y times modulus of gy, that is a positive function, and you can integrate that. Okay, it may be infinity, but doesn't matter. You can integrate any positive function always, right? But now you have you can apply Fibonacci's theorem, right? Because you are integrating positive functions, and Lebesgue measure is translation invariant. So if I integrate this function first, modulus of f of x minus y with respect to, let's say, dx, okay. So the minus y will not play any role because the Lebesgue measure is translation invariant. That is simply L1 norm of f, right? And what remains is integral of mod g, which is L1 norm of g. Okay, so this is nothing but L1 norm of f times L1 norm of g. Okay. So the one there simply means the L1 norm in Rn, which tells me that f convolve with g makes sense, right? It's finite almost everywhere, and the L1 norm of f convolve with g is less than or equal to L1 norm of f times L1 norm of g. Okay, so we have proved a simple inequality which will be used at most places. So we have f convolve with g, L1 norm is less than or equal to L1 norm of f times L1 norm of g, right? So you can always convolve two L1 functions and you will still land in L1. Okay, so that is the upshot of all that. Not just that, you have a certain inequality, okay, which makes L1 into what is known as a Banach algebra. Okay, so if you haven't heard the term, that's not it's not a problem. We'll know whenever it's needed. I'll define this formally and then we'll go ahead. But you can also look at this in a slightly different manner. You can look at this as, So, if I fix a function f in L1, okay, I can define this operator T sub f, right, from L1 to L1 to L1. Well, how do I define? Using the convolution. Take a G, right, Tf at G is equal to f convolved with G, right. I am fixing an f and I am looking at the operator G going to f star G. This is a linear operator, right. If I take G1 plus G2, then I will have f star G1 plus G2, which is from the integral definition, it is clear that it is linear, right. And this inequality tells me that the norm of Tf G is less than or equal to something times norm of G, which means that it is a bounded operator, right. So, Tf is bounded from L1 to L1, right, as a linear operator. So, it is a bounded operator and the operator norm of Tf, right, is less than or equal to L1 norm of f, right. This inequality is simply just that, right. That is another way of interpreting the convolution inequality. Okay. Well, we will actually see that the norm is equal, but that requires some more steps. More details on the space L1. So, we have one operation now, convolution, but Rn, well, Rn comes with lot of structure, so you can differentiate functions, right. There are functions with compact support, continuous and so on. So, when we will see how the convolution behaves with all such operations. Okay. So, all that will be needed in our in the course, and there are certain function spaces which are very important. I'll define them as well. So, let me give you some more exercises. So, if f is in L1 of Rn and G is in LP of Rn, okay, where P is between 1 and infinity, then the convolution, so f convolved with G, so we have defined that, okay, same integral, lands you in LP, okay, and the LP norm is less than or equal to L1 norm of f times LP norm of G. Okay, so if I convolve L1 with LP, I land inside LP, right. L1 with L1 goes inside L1 and L1 with LP goes inside LP with this inequality. So, you can interpret this again, right. I take a function in L1 and I look at the operator G going to f star G on LP. So, that is a bounded operator and the norm of that is less than or equal to L1 norm. Okay. Well, it need not be equal to L1 norm, we will see that later, but for L1 these norms are equal. Okay. So, well, this is not a difficult exercise, you can if you know what is Minkowski's integral inequality, you can use that. Otherwise, how do you get the LP norm of something? You integrate against something in the dual, right. So, you take a function h in the dual of LP, okay, integrate against f star G and then apply Holder's inequality, you will get this. Okay. So, we are using the fact that continuous linear functionals on LP are given by things in LQ, where 1 by P plus 1 by Q equal to 1. So, you can use that. Okay. So, second one, if f belongs to Cc of Rn, well, what is this? This is the class of continuous functions on Rn with compact support, right. Are you familiar with this? Okay, I will write it down. So, Cc, okay, if I have a function f from Rn to, let us say, complex plane, support of f is, you look at the points where f is non-zero, okay, and you take the closure of that. So, that is called the support of f. So, that is where essentially f is supported, outside that it is 0, right. Well, in our case they are continuous. So, Cc of Rn is simply continuous functions, continuous, and support of f is compact, right. So, outside a compact set it is 0, right. So, Urichon's lemma will tell you how to construct those functions, correct. So, the C here denotes the compact support. So, they are very nice functions, right? They are continuous and they die very fast. So, they are bounded, they are in all LP, so you can convolve them with anything you want. Okay. So, you take F in CC of Rn and you take G in LP of Rn for any P, then F convolve with G is continuous. Of course, it is in LP because this is in L1, so it would be in LP, there is no problem, but it attains some smoothness. So, I started with an arbitrary function G in LP and a continuous function with compact support, convolve them, I will get a continuous function. Okay. So, think of convolution as a smoothing procedure. Okay. So, well, this follows from usual DZT kind of argument. Okay. So, as long as the integrals are finite, you want to prove something is continuous, what will you do? You take xn converging to x, show that f star g at xn converges to f star g at x. You have integrals. How do you prove integrals converge? Use one of the limiting theorems. That is the only way, right? There are only 3 of them. Use one of them. Okay. 3. Well, if I take both of them to be nice, Cc of Rn, okay, then the convolution is also going to be in the same class. C of Rn. Okay. If I take 2 compactly supported continuous functions and convolve them, the convolution is also going to be compactly supported. Okay. So, where will, if you write down the integral, you will see this immediately. Support of f star g is going to be contained in support of f, which is compact, right, because f is in Cc of Rn, plus support of g, right. Support of g is also compact. So, if I add 2 compact sets in Rn, I will still get a compact set, right. So, that's an easy topology exercise. Maybe one more. So, if f is in LP of Rn, g is in LQ of Rn, okay, where 1 by p plus 1 by q equal to 1 less than to p less than or equal to infinity. You can still convolve them, that is purely Holder's inequality, right. Integral of f of x minus y g by dy. F of x minus y is in L1, LP, g is in LQ, so apply Holder's inequality, you will get a bounded function. Okay. So, f convolve with g L infinity norm less than to LP norm of f, LQ norm of g, right. This is simply Holder's inequality, there is nothing here. But if I leave out p and 1 and infinity, I get a much nicer function. Okay. So, if 1 is strictly less than p, strictly less than infinity, then f convolve with g is actually a C0 function, C0 of Rn. Okay. What is C0? Functions vanishing at, continuous functions vanishing at infinity. So, they die at infinity. Well, how will you prove something like this? You can start with functions in Cc, they are dense. So, okay, so use the fact that, so use Cc of Rn contained in LP of Rn is dense. Okay. So, this dense as long as p is strictly less than infinity. Okay. P equal to infinity, it will never be dense because convergence will be uniform and so everything in LP will be continuous. Okay. So, for p less than infinity, this is dense. So, you can approximate any LP function and any LQ function as long as p is between 1 and infinity by Cc functions. Okay. So, start with them, take f in Cc, g in Cc, convolution is a continuous function with compact support, and so it is in C0, right, because it dies at finite time itself, right. So, it vanishes at, and then you approximate, you change one of them into LP, other is still in Cc, but if this is in LP, I have a sequence of functions Fn converging to f in LP because Cc is dense, Fn's are Cc, so Fn convolve with G will be Cc, but if Fn converges to f in LP and I have a G, then you will have uniform convergence, just use this inequality. So, Fn convolve with G are CC functions, in particular C0, and they converge uniformly, so the limit will also be there. Okay. So, what you have done is, starting from two continuous functions with compact support, you have gone to one function being general and other function being compact support. Now, you can go do this one more step, approximate the other function with continuous functions with compact support and use the previous step. Okay, so, do it in two steps. Okay, well, if you want to do it in one step, you can do that as well. You can start with fn's converging to f, gn's converging to g, right? Fn's are in CC, gn's are in CC, and use this inequality that will give you immediately, but you can do it in two steps as well. So, I'll leave it to you. Okay, so some of these are not difficult, but you should do it once too, so that you are comfortable with the spaces LP. Okay, that's very important for Fourier analysis. You need to know which function belongs to which class. Okay, so that is the first thing I started with, right? Mod x to the a, mod x to the minus a. These kind of functions will come up in analysis very many times, and you need to know where they belong to. Okay, because most of the time you will be looking at convolution operators or properties of convolution operators and so on. For that, this kind of knowledge is important. Okay, so let's get back to L1, and so recall that we defined convolution here, right? So I have f convolved with G, L1 norm is less than or equal to L1 norm of f times L1 norm of G, right? So this makes L1 into a Banach algebra. It's a Banach algebra. Is the term familiar to you? No. What about you? Nobody knows this. Okay, I'll define what a Banach algebra is. Okay, so let's keep this here. We won't need any properties of the Banach algebras right now. Okay, we'll look at it from the Banach algebra point of view at some point of time in the course. Okay, not now, but let me define what it is. So, whenever, well, what is an algebra? An algebra is a space with multiplication. Okay, Banach algebra would mean it's a Banach space where there is a multiplication. Okay, but you want the multiplication to be continuous. Right, that's the only extra condition, and that's precisely this inequality. Okay, so let's start with let's say B, script B. Okay, so this is a Banach space. Banach space. So that means there is a norm. It's a vector space. There is a norm with respect to which it's complete. There is a multiplication. So with a multiplication, okay, that's what makes it into an algebra. You can multiply things. Well, what is a multiplication? That would be a map from B cross B to B. Right? You take two elements in B, you should get another element in B. Okay, so that's a map from B cross B to B. We'll simply denote it by x comma y going to x times y. Okay, so if you want, you can put a star or circle or whatever, some notation, but with the property that, so we also need, for it to be a Banach algebra, you want this to be continuous, okay, which means that norm of xy will be less than or equal to norm x into norm y. So norm of xy is less than or equal to norm x into norm y. So all this is for all points in the Banach algebra. Okay, such a thing is called a Banach algebra. Okay, so B will be a Banach algebra. So there is a multiplication which is continuous. That is all is there. L1 is a Banach algebra with convolution as multiplication. I take f and g, multiply them, not pointwise. Okay, multiplication is star, f star g. So x comma y going to x star y. That is my multiplication, and here it would be x star y L1 norm less than L2. Right? That's precisely the inequality we have. So the convolution makes L1 into a Banach algebra. Okay, so that is the upshot of all that we said. Well, whenever you have multiplication, one question you want to ask is whether there is an identity. Right? That's what you do with groups, which means if can I get a G such that f star G equal to f for every f, right? That is what you mean by an identity. Okay, well, we don't have an identity. What we have is an approximate identity. Well, we don't have an identity is something you will see immediately after we define Fourier transform and its properties. You can prove it directly, slightly messy proof, unless the group is discrete you do not have an identity, but that is a different topic altogether. But using Fourier transform it can be proved very easily that there is no identity. So, right now I will only state it and then we will justify the term approximate identity. Approximate identity. So, let me write this as a fact that there is no identity. So, fact there exists no identity for the Banach algebra L1 of R. Okay, that is there exists no G in L1 of Rn, okay, such that f star G equal to f for every G in every f in L1 of R. So, as I said we will prove this using Fourier analysis. Okay. So, right now you can look at this very closely and then try to say that the support of G will be in smaller neighborhoods of identity and so on and so forth, and then conclude that G will have to be 0 almost everywhere, but then this will not be true. But that's a slightly messy proof. Neater proof can be done, can be given using the Fourier transform. So, after we define the Fourier transform and look at some properties of it, it will be immediate that there is no identity. But we can get approximate identities in the sense that we can get a sequence of functions which will converge to whatever the identity should be. Okay. Well, so if you know enough measure theory, you should know that if I take the Dirac delta at 0, then f convolve with Dirac delta at 0 is f, right? Okay, let's justify that. So, remember our definition of f star G is f of x minus y gy dy, right? So, instead of gy dy, if I had a measure d mu y, this will still make sense, right? So, if mu was the Dirac at 0, so if you take mu to be delta naught, are you familiar with this? This is simply the measure supported at 0. It is 1 there and 0 everywhere else. So, if I take a Borel set, its measure is 1 if it has 0, otherwise it is 0. So, it is supported at 0, right. So, the integral will be just evaluation at 0. So, that is f of x, right, y is 0. So, this would be f of x, and that is precisely the identity property. So, if I include the measures, then there is an identity, okay. So, but there is no function which will do this, okay, that is the point, alright. But you can get functions which will approximate this measure, that would be the approximate identity. Okay, so, let's define that. Okay. So, let phi be a function in L1. Okay. We will take phi positive, it is not necessary, but let's take that, and integral of phi is 1. Okay. We are going to construct approximate identity out of any positive function whose integral is 1. Define, okay, phi sub epsilon at x equal to 1 by epsilon to the n phi of x by epsilon. Okay, so, epsilon for epsilon positive. So, epsilon is a positive number. For each epsilon positive, we define phi sub epsilon to be 1 by epsilon to the n phi of x by epsilon. So, this is called a dilation. The original phi is sort of dilated. Okay. For example, think of phi as something which is supported in the unit interval on the real line. Okay. Then phi of x by epsilon will be supported in the interval minus epsilon to epsilon, right. You want modulus of x by epsilon to be less than or equal to 1. So, that is same as saying mod x is less than or equal to epsilon. So, it is supported in minus epsilon epsilon. So, as epsilon goes to 0, the support decreases. But because of this 1 by epsilon, that the total area will still be the same. So, it sort of finally concentrates at 0, the whole mass gets concentrated at 0. That is precisely that measure. So, this kind of functions will actually converge to that measure. So, they act as approximate identities, not identities. So, what do I mean by approximate identity? If I look at f convolved with phi epsilons, they will converge to f. We do not have a g such that f star g equal to f, but we have a sequence of functions such that f star epsilon converges to f. Okay, so, that is what we mean by an approximate identity. Okay, so, you can think of this as a theorem if you like. F convolved with phi sub epsilon converges to f as epsilon goes to 0 in L1. Okay, so, this never becomes f, but it converges to f. Okay, so, the collection of functions phi sub epsilon approximates the identity. So, this is a easy proof. I will write down 2-3 lines to justify this. So, let us start with integral over Rn f star phi epsilon, right. So, this is f of x minus y phi epsilon y. So, that is in 1 by epsilon p of y by epsilon dy, right. This is the definition. So, let us change variables. So, we will instead of y by epsilon, let us put something here, and so what will happen to the epsilon? There is a 1 by epsilon n, right. So, y by epsilon, the Jacobian will be 1 by epsilon dy, right. Multiplying by epsilon is a linear map. Well, here I am multiplying by 1 by epsilon, that is a linear map. So, its Jacobian is just the determinant, that is 1 by epsilon to the n, that is here. So, that goes away, but y becomes epsilon y, right. So, if I change the variable, I am going to get integral over Rn f of x minus epsilon y phi y dy, right. So, well, if you want to do this in the usual way, you put y by epsilon equal to t, right, then 1 by epsilon to the n dy equal to dt, and then you change variables, right. Rn does not change, so you will have this. Now, I am trying to prove that this converges to f in L1 of Rn. So, let us subtract f and see what happens. So, f convolved with phi epsilon at x minus f of x. Okay. Right, I want to know if this goes to 0 in L1, right, because I am trying to prove that this converges to f in L1. So, this should go to 0 in L1. Well, first of all, this is nothing but, well, we have changed the variable to be this. Remember, the phi has a property that its integral is 1, right. So, I can write this as integral over Rn f of x minus epsilon y minus f of x, right. Remember, the x has nothing to do with the integration, phi y dy, because integral phi y is 1, right. So, f of x comes out. So, this can be written in this way, clear. So, now, well, instead of writing down again and again, I will use take the advantage of the board. So, take modulus, that will be less than or equal to modulus of this. Phi is positive, so I will put phi outside. Okay. Well, I am not done. I want to prove that this converges to this in L1 norm, right. So, let us take the advantage of the board again. So, how do I take the L1 norm of this? Simply integrate, right. So, okay, let me forget this, and I will say L1 norm, right. So, I have integrated with respect to Rn. Well, I will have one more integral here, Rn and dx, right. Well, what is this? So, this is equal to, so I again positive functions. So, Fubini's theorem applies. I can integrate with respect to x first. When I integrate it with respect to x first, I am going to get the L1 norm of this difference, right. So, I will have integral over Rn, okay, I have a phi y dy here, and I am integrating with respect to x first. What do I get? I get the L1 norm of this function. So, let me write this as L1 norm of f of, well, I will not write x, it is dot minus epsilon y, correct, minus f dot, right. It is the L1 norm in the dot variable, correct. So, now this should be familiar to you. As epsilon goes to 0, this epsilon y goes to 0. So, this is simply the continuity of the translation in L1, right. So, this whole thing will go to 0 as epsilon goes to 0, right. You are familiar with that, right. F of x plus h minus f of x L1 norm will go to 0 as h goes to 0, right. Translation is continuous in L1. So, this pointwise goes to 0, it is bounded by 2 times L1 norm of f, and I have an integral with respect to phi which is integrable. So, by dct the whole thing will go to 0, right. So, the whole thing goes to 0 by dct. Okay. So, I have skipped some steps, but they are all straightforward measure theoretic arguments. What we have is an approximate identity. Okay, so this is very important in Fourier analysis. Many of the times we will use the approximate identity arguments to prove various things. So, let me repeat this. I do not need positivity, okay, because I can take modulus of phi here, okay, but most of the approximate identities we use will be positive. Main thing is the integral is 1 and we dilate. So, dilation is something which you should understand, phi of x by epsilon and 1 by epsilon to the n. So, this makes the integral to be 1 always, right. This is because I am multiplying by the Jacobian of the transformation here. Okay. So, when I integrate this, this is simply the integral of phi. So, the integrals are all 1, but if I look at phi as something which is supported in the unit interval, the dilation makes it supported in minus epsilon to epsilon, but the integral is 1. So, it will you may start with something like this, but as the interval becomes smaller and smaller, the area under the curve has to be still 1. So, it will keep increasing. So, it sort of finally puts all the mass at 0, which gives me that measure. Okay. So, that is why the approximate identity happens. All right. Okay. So, this proves the theorem, and we will stop with writing down some exercises. So, if f is in L1, sorry, LP of Rn 1 less than to p strictly less than infinity. So, here we proved that everything converges in L1, you can lift it to LP and phi exactly as before. So, phi was positive, integral over Rn phi x dx was 1, and we have the dilation phi sub epsilon, right, equal to 1 by epsilon to the n phi of x by epsilon. Okay. Then, well, f convolved with phi epsilon still makes sense, right. F is in LP, phi is in L1, phi epsilons are also in L1. So, I am convolving L1 with LP, L and in LP, right, that was the previous exercises. Converges to F, this happens in LP. Okay. So, the approximate identity part works in LP as well, and the proof is exactly the same. Okay. Well, if you look at this proof, what did we do? We wrote down f convolved with phi epsilon, changed variables, we got this, then we subtracted f, right, and then we took L1 norm. Instead you take LP norm, right, apply Minkowski's integral inequality, you will get LP norm of f, and translation is continuous in LP as well. Okay. So, same proof works. Okay. So, there is no difference. Okay. But you see that I have left out p less than infinity. Well, for p equal to infinity, the better space is C0. So, let me write down that if f is in C0 of Rn, then f convolved with phi epsilon converges to f uniformly. Okay. So, uniformly means in L infinity, right here. So, that is a substitute result for L infinity. Okay. Well, another exercise 3, if f is in LP of Rn and integral over Rn f times phi is 0 for every phi in Cc of Rn, then f is 0. Well, this is not, this just follows immediately from whatever you have done here, because if it is 0 for all phi, you can dilate, you can take one phi from that approximate identity, dilate it, translate it, it will all be 0, because phi will be still in compactly supported continuous function, and when you translate and dilate phi, you are going to get phi sub epsilons, and this will become f convolved with phi sub epsilon, right. This is fine. What I mean is, I have for every phi, right. So, take one phi and look at the function phi x minus y by epsilon, right, 1 by epsilon to the n. This is also a continuous function with compact support. If I integrate f against this, it is 0, that is a given condition. But when I integrate f against this, I am getting phi convolved with phi sub epsilon. So, f convolved with phi sub epsilon is 0, but that is supposed to converge to f, so f will be 0, right. So you, I mean, in a sense, f is determined by its integrals against a dense subspace. So that's okay. So now it's the next lecture.